And then we're going to number 2. Particles' two-dimensional motion can be modeled by the position function vector e to the power of t squared and then cosine squared t. So it says find the velocity vector of the particle at t equals 3. So since that's the position, which means we're taking the derivative, so e to the t squared derivative is 2t e to the t squared, and then cosine t would be 2 cosine t, and then sine t negative. So this would be the velocity vector. And then at 3, right, 3, yeah, 3, you can plug this back in. So 2 times 3 times e to the power of 9, which is around, yeah. And then negative 2 times cosine 3 and then sine 3 would be around 0.279. Okay, so we're going to say around. This would be our velocity function. Okay, the next is what is the acceleration of the particle at t equals 2? So acceleration is, which means, okay, and simplified. Okay, so this is what we got for acceleration. And then particle at 2, so we need to determine the acceleration. For this one, we need to do 2 times the power of 4. Okay, so we got 982.767, and then we got this one. Okay, and then since we need to find the acceleration, not the acceleration vector, we're going to square the first one, well, a of x and then a of y. So a of x squared plus a of y squared, and square root that would be the acceleration at 2, which means we're going to have to square so we got 989.768. Okay, so here is the acceleration. Okay, and then this part C reads, find the value of t where the particle is completely at rest, if any. So this means when both parts of the velocity vector are equal to 0 at the same time. Okay, so I guess like the velocity in the x direction and the velocity in the y direction are both equal to 0. But then we see that one is e to the power of t squared, and then one is cosine squared t. And then this one, also you're specifying this in the interval between 0 to 4. But then we see that the general graph from 0 to 4 shows that e to the t squared is just shooting upwards, and then cosine t squared is more going here like that. Oops. Like that. So we don't really see the e to the t squared actually reaching 0. So it's an exponential function, so it's going to be growing like infinitely. So that means that doesn't reach 0 at any point in time. So the particle is actually never completely at rest. It is never completely at rest. Equal to 0. Yeah. Alright, so that's part C, and then it says for part D, find the speed of the particle at t equals 1. So speed of the particle, you can use, since you know the velocity vector to be et squared and cosine squared t. So speed is actually going to be this one, like the first part, vx and then vy. So vx squared plus vy squared, and then square root of that, because speed again is magnitude, so we're doing the square root. So let's just find this first. V of 1 equals e to the power of 1 plus cosine 1 squared. So adding these two, so the answer is 2.771. Yeah. So the speed of the particle at t equals 1 is 2.771, and then velocity at 1 is equal to 2.718 and 0.540. Yeah. Okay. Yeah, that was it for particle motions.